Hello everyone. So first of all, I apologize for the late update since last Thursday. Um, Today we're going to learn about the independent events. So previously, remember all the events we discussed and all the experiments we discussed are single, which means there's only one step. Um, for example, let's see if we toss a single coin or we rolling many dice or rolling a dice many times. We all treat them as single experiment, which means we include all the possible cases in one sample space. Like if we rolling two dice, the sample space equal to some two-dimensional tuples 1 1 1 2 1 3 2 1 until 6 6. So there's like 36 different cases in that set. And if we toss in a coin n times, we have all the sequence of h and t of length n, which means there's n tuple of the events including in that sample space. But this is not always the case if we try to explore more advanced and more complex cases. For example, why not? Because we are tossing coin n times, and if like each step or each time we toss a coin, uh, their uh, their possibilities are very similar or exactly the same. Why not? We can treat them as a tossing a single coin and just with different times, like this one. Tossing a single coin is like it's have two elements in the sample space, the h and t. And why not we do something with that smaller sample space? So this is what we are going to talk about today. And and first of all, we need to we need to know one point. That is, we like to not have to answer all future experiments. Build a simple sample space for that, and we can build multiple experiments with one sample space, but like transform it somehow to represent our chains of events. First of all, let's talk about independence. Independence is very important. So in life, we say if one person is independent of something, we say he doesn't need others' help. He's able to do all the things by himself. So this is the definition of independence in real life. But in mathematics talking, in probability field, independence it simply means two events or even more events. But here we talk about two events, A and B are independent of each other if the occurrence of A does not alter the probability that B occurs, which means like if something A occurs and it's already occurred, but event B, the probability that B occurs is not influenced by the A. So yeah, this seems a little bit abstract for now, but we'll see more examples and to understand it graphically later. So we first say the independent events. The definition is a more precise definition is here. So uh, the probability triple we first define that, and two events A and B are on this probability triple are independent if the probability of A intersection with B is equal to probability of A times probability of B. So this is a general rule for us to testing if two events are independent or not later. And so why that is the case? So first of all, we ignore this statement and first look at this graph. So this is imagining the rectangle, the larger rectangle outside is this is a uniform a universe set, and we can find and we use a straight line to cut the universe set into two parts, A and a complement of A, and also we have an ellipse in the center. We say it's event B, and so for now the event A intersection with B is by the Venn diagram theorem. It is this set. It is the set that both containing A and B. So it's here. So how can we say like event A and B are independent or not? There's only one thing we need to check is to see whether A intersection with B divided by the area of A is equal to B divided by the area of the omega. So that's how we test independence, because if that's the case, A is not influenced. If A occurs, the probability in A is the same as the event B, the probability of B, the entire B in the entire sample space. So this is the test for the independence. And so you may say, oh well, this you said just now is very reasonable, but what to do with this formula? It doesn't look right because we were doing dividing, but here is a multiplication of two probability. So what we are doing here is to use Laplace experiments definition and to see this formula is actually derived from this graph. So based on the Laplace experiment, the probability B is the cardinality of B divided by the cardinality of omega, which is here. And probability similarly, we can define probability of A and probability of A intersection with B. We can all define that here. And what I said just now, use your brain to think about, like the probability of A, this area is A intersection with B divided by A is to, let's see, is A intersection with B divided by, is this term divided by this term, right? So yeah, this term, the entire term of here. And we can simplify the cardinality of omega out. So it's A intersection with B divided by A. All right, so that's not a big deal. This is very easy to see. And another side, we say what's equal is the B is the probability of B in the entire sample space. So that is very easy. That is B divided by the sample space. So we got this formula here. So it's A intersection with B divided by A is equal to B divided by omega. So this is what we derived. And we just need one very simple transaction to make it possible. So remember, what we want to find is this one. And what about if we times it out, like how to say, we times let me see, okay, so what about we times of cardinality of omega here and times the cardinality of A here. So that becomes A intersection B times omega is equal to A times B, and that is the principle of multiplication. And if we down that, we say divided by the whole term by two times okay, by the cardinality of omega square, and this term becomes A intersection B divided by omega, this one, and this term, because we divided by omega square, so we have two omega in the denominator, and the numerator is A times B. So it's this term. And tracking back to the definition of the Laplace experiment, PB is equal to this term, PA is equal to this term, and PA intersection with B is equal to this term. So because we say these two terms are equal from this formula, we proved this one, and exactly the same as the formula above. But usually this formula is in the definition, but in some realistic examples, maybe this is not easy to see. Maybe this is not easy to calculate based on what we have. And this formula is also very important, as we derived here. Cardinality of B intersection with A. Okay, so this is a different term, but we can use we can use the exchangeability of the intersection to say they are just equal. So B intersection with A divided by A is equal to B divided by omega. So we are done. So so this formula and this formula is also equal. I would say equally important in realistic problem. So why not? Let's see example to see how the independence is working. So if we roll fair dice, okay. I think it's dice, not die. Probably okay. And consider event A as even number and B as number is a multiple of 3. And we want to see if the two terms are independent or not. Okay, so the sample space is common. It's 1, 2, 3, 4, 5, 6 terms, 6 faces of dice, and A is equal to, because it's even number, is 2, 4, 6. The multiple of 3 have 2 cases, 3, 6, and based on this, we can already calculate the intersection with A and B. This is a new set with common element between all in both in A and B, and this is 6. This is very simple, as we can easily see. So now we can, because we got this set, the cardinality is 1, and because of the cardinality of the sample space is 6, the probability of A intersection with B is 1/6. It's here. All right. So what about like probability A is 3 divided by 6 is 1/2, and probability of B is 2 divided by 6 is 1/3. So based on that formula, above here, we only need to do one thing to prove they are independent or not, is to times these two terms together to test whether it's 1/6, the P of A intersection with B. So are they independent? This is very simple, because 1/6 is equal to 1/2 times 1/3. So we have proved that they are independent actually. So the answer is yes. So let's see some more examples. Okay, so now we toss a coin twice. The coin has 2 sided. So let H1 is an event. T1 is also an event. That is, the first toss is the head, so we denote it by H1. If the first toss is tail, we denote it as T1. So similarly, if the second toss is head, we say it's H2, and second toss is tail, we say it's T2. So we define a new event here is E. So E is equal to H1 intersection with H2, T1 intersection with T2, and the union between them. So this means, this is very interesting to see. So it only has 2 cases actually, because whether the first and the second coin toss is both head, or the first and second coin toss is both tail. So in this case, H and so in this case, E only have 2 events, that is HH and TT, because union doesn't require it to be exactly in both of the 2 set. So E is also means the 2 tosses are equal. So HH and TT. And the first question we want to ask is that, are E and H1 independent? So first, let us examine through the formula we have above. So first of all, the sample space have 4 elements: HH, HT, TH, and TT. The H1 has 2 elements: HT, HH, and E has HH and TT. So H1 intersection with E is equal to HH. This is the common element they share. So now we have, now we can calculate PH1 is equal to 1/2, P is also 1 over 2. So if we time them together, it's 1 over 4. And because H1 intersection with E is also equal to 1 over 4. So in this case, we say the probability of E intersection with H1 is equal to probability of H1 times probability of E, and they are equal. So by this formula, we can say they are independent. We have already proved that. There's more question to ask about. So the second one is if event E and event T1 are independent. So this will be very similar to this one. So let's see what's T1. What's in the set T1? T1 has TH and TT, and E has HH and TT. So the common term they share is TT. And just because TT there's only one, so the probability of E intersection with T1 is equal to 1 over 4, and because each of them is the probability of both E and T1 happening is 1 over 2. So 1 over 2 times 1 over 2 is 1 over 4. So they're equal, so independent. And what about H1 and T2? So H1 has two terms, that is H1 that is HH HT, and T2 has TT and HT, and they share one term. So based on the pattern above, we can easily say they're independent. We don't need to because like usually this is also independent of 1 over 2 times 1 over 2 is equal to 1 over 4, and the intersection itself is 1 over 4, so they are independent. And we would like to see more examples about so let's think about this one. H1 and T1 are the independent. So what's in H1? H1 has HH, HT, and T1 has TT and TH. So one thing we observe here is all the elements in H1 has H in the first place, but all the elements in event T1 has T in the first place. So they are like a pairwise destroying event. Those two events share no elements in common, so the intersection with H1 and T1 is nothing, it's empty. Thus, the probability of H1 intersection with T1 is 0. However, because each of those two events have probability 1 over 2, so if we time them together, it's 1 over 4, but 0 is not equal to 1 over 4. So as a result, we can say probability of H1 is times probability of T1 is not equal to probability of H1 intersection with T1, so they are not independent. So this is this test we can also say some events are not independent, or not all events are independent, and actually in reality, very few events are independent, like 100% independent, and most of the events have slightly dependent variable or dependent property inside. But if it's very little, we ignore that in reality. So proving two events independently is very ideal. I would say very ideal in coin toss, in dice, and some like very easy game. They're independent. But if you say like if the day is cloudy and cloudy weather is related to tornado, I would say you cannot prove that is independent, but it is not independent because there are too many variables to consider, and we are not able to count them one by one. So based on this, we can say H1, H2 are independent. Okay, so let's left this as an example for you to examine. And I would say yes, because obviously in this example's pattern, 4 elements, and H1 and H2 shares one thing common, that is how to say they share HH in common. So obviously it's independent. And there's more cases we should consider, like are E, H1, H2 independent. So this is not a example of two events examining their independence. There's three events, and how we can prove this? We have different formulas to proving. So let's see if E intersection with H1 intersection with H2 is equal to PB times PH1 times PH2. Is that, if we can prove that, is that enough? I would say if it's not equal, then it is not independent. But if it's equal, it's not 100% sure to say it's actually independent. So we just compute that, because H1 E intersection with H1 intersection with H2, we have one element in common, that is HH. That's the one and only terms they share, and the probability of HH is 1/4. Okay, so that is 1/4 because we have 4 elements in total. However, if we times PE times PH1 PH2 together, we get 1/2 to the power of 3, so it's 1/8. So it's not equal. So now we can conclude that E, H1, H2 are not independent. And there's a small note of small notation here. Even though H1 and E and H2, H1 and H2 are independent, which we have proved before, like E and H1, E and H2 we have not proved, but we can prove that, and H1 and H2 are independent. So only question we left undoubtedly is E and H2, but E and H2, if we intersection them, we have one term in common, that is HH. And each of E and H2 have probability of 1/2. So yeah, so they're independent. Even though the 3 separate events are independent, we are not able to say they are independent for the 3 events. Okay, so let's see the formal definition of independence of more than 2 events, 3, 4, 5, until to the dimension of n. Preceding example shows that pairwise independence is not sufficient for more than 2 events to be independent. So we give a definition here. So for the events A1, A2, A3 to the AN are called independent if for each k and inside the natural number set 1 to n, and each of the collection of indices 1 smaller than I1, smaller than I2, smaller than Ik, smaller or equal to n. We need to prove the probability of intersection of these terms are equal to the multiplication of each of the single events multiplication. The multiplication of each single event's probability. And so what does this mean? It means that if we want to examine I1, for example, we say there's 4 elements. Okay, there's 4 elements. So what we need to prove? We need to prove if one. So the I1 Ik here can be so k. What can k be? K can be 1, 2, 3, and 4. So we first want to show like probability of in the case of k equal to 1, there's probability A1 equal to probability A1, A2 equal to A2. That's obvious because this is exactly the same term. So let's move to k equal to 2. So A1 intersection with A2 is equal to probability of A1 times probability of the A2. Okay, that's exactly what we do for the 2 events. But what about k equal to 3? We need to prove all the cases of like A1, A2, A3, A1, A2, A4, A2, A3, A4, and A1, A3, A4. These 4 terms, we need to prove them one by one. And also for k equal to 4, we have A1, A1, A2, A3, A4's intersections probability equal to the probability of each of the 4 single events probability. Okay, so let's see. That seems very tedious, or that's a circumlocution for calculating all of them. And this is, and remember, this is only 4 events. If there's 5 events, 6 events, it will goes to infinity very quickly. And this is because we have in totally 2 to the power of n equalities have to hold. Because for each of the events, A1, we can say it's inside or outside. And for A2, it can be inside, outside. A3, it can be inside or outside. So for each of the AI, we have 2 possibilities, whether it can be counted in our examination or out of examination. So if there's a n of the single events, we have 2 to the power of n. We have like 2 times 2 times 2 for the n2. So that's 2 to the power of n equalities we have to check. And that is really not impossible. That is not really possible in reality. We don't have enough time to calculate all of them. And usually for the events, there could be 5, 6 or more events. And that will be impossible if you only have like very, very limited time to examine all of them. So what we do with independent in reality is not to calculate them, it's to see by common sense. Like drinking of water is really related to the weight increase. That's right. But if you let me think of like an independent event. For example, if a person named Jonathan take a train today, is independent of a man named Akatsuki in Japan who go to sleep before 8. So these 2 events are not really likely to be dependent. So we can obviously say they're independent event, but how can we prove that? We are not able to prove that. So that's the difference between idealistic independence in mathematics and what the real case is. That's a big difference. And so what we are doing today is to get a sense of what's independence. Once we define it using the wisdom of mathematics. But in the realistic research, you might not find it really helpful. But what we'll talk about next week, the conditional probability, that's more useful than independence. But independence is a prerequisite to check for the conditional probability too. And if you're dealing with data, you can use RStudio to draw a graph. For example, like there's some residual plot to see if they're independent or not. Okay, and there's another useful lemma for us to prove. Let's say if we already know A1, A2 to the AN are independent events, and there's another set of events B1, B2 to the Bn. And there's a property of the events B1, B2, B3 to the Bn. That is, for each of the Bi is equal to Ai, or Bi is equal to Ai's complement. Then we can say the events B1, B2 to the Bn are independent. This is also a very useful theorem to use in probability field, because usually the some question asks like we already know a set events are independent, but what about its complement? The complement is also independent. And so if they ask us about a question of its complement, we can use the property of independent events. And how we can prove that? So first of all, because it's the BI is equal to AI or BI is equal to the AI complement, we can say we can first give a trivial case like only A1 is equal to the complement of only B1 is equal to the complement of A1, and all other terms A2, A3, A4 they are equal to the B1, B2, B3, BK. And so what we want to prove is to prove the probability of A1 complement intersection with A2, A3 to AK is equal to the multiplication of those probability one by one. So this is what we want to prove. And so let's begin. So because first of all, we can use the probability, use the property of complement of A1. So this is the complement of A1 is equal to omega minus or the difference between omega and A1. And so now we also use we also combine the later terms together. So those are in a bracket. Okay, imagine those are in bracket. So there's only two terms, the difference between omega and A1, and also A2 intersection to AK. And because this is a single term, we can use the distribution law to distribute it out. So the first one is the first term becomes omega intersections A2 to AK minus probability of A1 intersection to AK. And in this case, because like the omega as a sample space it is the universe set, so we can ignore this term. So A2 intersection to AK minus probability of A1 intersection to AK. This is equal to the first term we defined. And because we already know that all of the AI are independent, this is the independent assumption the question already gave us. So this is equal to probability of A1 times A2 times A3 times A4 times 2AK minus A1 times A2 times 2AK. So we can extract one term out, that is 1, and 1 minus the probability of A1. So we can extract 1 out, and here extract probability of A1 out, and this becomes the first term. And all of the terms like probability of A2, A3, A4 to AK, this single term can be the common factor. So we separate them out to get this term. And obviously, based on the definition of the set difference or complement, 1 minus a set is equal to the probability of its complement. So A1 complement times PA2 times PA3 times until PAK is equal to this term we defined above. So actually they're independent. So we already proved B1 to Bn is independent if B1 is equal to the complement of A1 and all of the other bits Bi is equal to AI. So So now, because this is only a trivial case, we cannot say by now we cannot say like bi is equal to like all of the b are independent if for any of the bi is equal to ai, or bi uh bi is equal to ai, or bi is equal to ai complement. But however, if we because this is trivial case, we can also change like A2 to be complement or A3 to be complement, and to change it one by one, and or we can show A1 to the complement and A2 to the complement. They are all the same. For example, if A1, A3, A6 are complement, but okay, so let's see if B1, B3, B6 are equal to A1 complement, A3 complement, and A6 complement, and all other BI is equal to A1, AI, then we have more terms like this. And we can also by the laws of of commutability, we collect all other terms together and left this term out, left those difference term out, and we will derive it one by one and get to this formula in the end. This is because if we have like difference between omega and ai for some I, and we will minus those term out without minus those term out without with three or more omega here. And in this case, the omega just ignored. So we have one minus one. So we can extract many ones out, as many as we want, to minus the terms in the second multiplication, but not in the first multiplication set. We can minus like 1 minus p a1 minus times 1 minus p a3 minus 1 times 1 minus p a6, and all other a are listed here. They are not influenced by the 1 minus term, and all the 1 minus term can change to the complement of a of a1, a3, a6, or any other number of a, and we get this term in the end. So we proved we can prove the checking for independence formula is actually an equality for any of the bi is equal to ai complement or bi is equal to ai. So this theorem we already proved that. And let's see another example here. Is the use of independence. Suppose a system consists of 5 independent components, C1 to C5, and they're connected as below. So C1, C2 are in a union. C3, C4, C5 is in a union too, but between C1, C2, and C3, C4, C5, they are not in union. They're in a chain. And if the probability that each component work properly is 90%, what is the probability that the system works properly? So how do you solve this one? So first, we want to write CI to say that the complement of CI works. So CI C1 or C2 means C1 or C2 or both of C1 and C2 works. We denote it by C1 union with C2. And we define it as D1. So D1 is this union works. The first union works, and T2 is the second union works. So C2 is equal to C3 union with C4 union with C5. And so what's the probability of D1? D1 is equal to the probability of C1 union with C2, and here we have 1 minus probability of C1 union with C2 to the power of complement. So what this means is 1 minus probability of so what this mean? Because this is a set of C1 union with C2, and C1 union with C2, this term is if we do a complement of it, and 1 minus the complement is a complement of the original set, so they are equal. And we can use the De Morgan's law to separate the terms out. So it's 1 minus p C1 to the power of C1 complement intersect with C2 complement. And remember, C1 and C2 are independent because all of them are independent. So C1 and C2 are independent. Then C1 and C2's complement are independent. So 1 minus p C1 complement intersect with C2 complement can written as 1 minus p C1 complement times p C2 complement. This is using the independence theorem above. And because C1, the probability of C1 works is 90%. So the probability of C1 complement works is 1 minus 90% is 10%. So it's 0.1. So we can see this as 0.99 because it's 1 minus 0.1 square is 0.99. And also the probability of D2, remember is probability of C3 union with C4 union with C5. So this is C3 complement intersection with C4 complement intersection with C5 complement, 1 minus those, and this turned out to be 0.99. And the system works. So how can we know the system works? So it must be C1 and C2, this union works and the second union works. So it's equal. So the probability that the system works is probability of D1 and D2 works. So it's D1 intersection with D2. And remember, because C1, C2, C3, C4, C5, they are all independent. So because D1 is equal to C3 union with C4 union with C5, and like D1 is equal to C1 union with C2, and because they are all in the intersection form, and if the original C1, C2, C3, C4, C5 they are independent, then its complement C1, C2, C3, C4, C5's complement is also independent, as we can and this is a result based on the lemma 3.12. So in this case, we can see the probability of D1 intersection with D2 can be written as C1 intersection with C2 complement times P C3 C4 C5 intersection and their complement. So in this sense, we can say they are actually independent. So because of D1 complement and D2 complement, they are independent. So its complement of complement, which is D1 and D2 itself, is also independent based on the same lemma 3.12 here. And finally, we can use the property to calculate. So the probability of the system works is P D1 times P D2, and this is 0.99 times 0.999 bar. So we can get the solution for this system example. Okay, so that's all for today. We discussed about independent events, and I would say the main goal for this lecture is to understand what's independent events, and how we can see from questions how it works in if asked like two or at most three events are independent, so how to prove that mathematically. And this is a prerequisite for our discussion next week, that is multi-stage experiments and conditional probabilities, because in some multi-stage experiments, we always want to see if the first step is independent of the second step or independent of the third step. And if they're independent, we can just times them together. But if not, if it's not independent, we have more to do. That is, we'll use some properties in conditional probabilities, and also do not always try to prove independence in realistic problems. Sometimes we can assume it independent by common sense, because not all events can be proved. All right, so that's all about today.